So my dear student friends, welcome back to my next lecture, that is the module number 14, and in the last 5 modules we have discussed about necessity of mass transfer coefficients, different ways of estimating mass transfer coefficients, and estimation of mass transfer coefficients. So what we do in this module now, we will solve some problems related to the estimation of mass transfer coefficient, so that you can understand how to estimate mass transfer coefficient. Then we can also understand how to estimate the flux. So what I will do is I will just read the problem, then I will try to solve the problem so you can follow the problem. And the first problem is, in an experimental aerated contactor, pure CO2 is being absorbed in water at 25 degrees centigrade and at 2 atmospheric pressure. Water is pumped into the contactor at a rate of 1 liter per minute, and the carbonated water leaves the vessel continuously so that constant volume is maintained in the contactor. The outlet water contains 2.3 grams of CO2 per liter. The specific interface area of the gas liquid inlet is 80 meter square per meter cube of the liquid dispersion. The volume of the gas liquid dispersion is 8 liters. The liquid phase can be assumed to be well mixed. At 25 degrees centigrade, the Henry's law constant per CO2 is 1640 atmospheres per mole fraction, and the diffusivity in water is 1.92 into 10 power minus 9 meter square per second. Calculate the thickness of the liquid film if the film theory is applicable. Next, the contact time between the liquid element with the gas if the penetration theory is applicable. Then the fractional surface renewal rate if the space renewal theory is applicable. So here what it is given, we are using some reactor vessel where we are passing a CO2 to make it as a carbonated water, and the liquid is continuously flowing inside that vessel, and the gas is also flowing inside the vessel. So there is a contact of gas and liquid. Then we are getting a pure CO2 and that is undissolved CO2 as gas stream, and we are going to get a liquid that is nothing but a water which contains about the carbonated which contains about the carbon dioxide. So what I will do is I will put it everything in the picture form so that you can understand what we are talking about. So here this is the vessel, and here we are passing pure CO2 gas, and here we are passing water, 1 liter per minute of water we are passing, and we are going to get water 1 liter per minute contains 2.3 grams of CO2 per liter, and undissolved CO2 gas is coming out as a CO2 out, and we have gas bubbles and the liquid is there. There is a contact of gas and liquid, so your CO2 is dissolved into the liquid, and this is 8 liters of dispersion. It is given that Henry's law constant per CO2 1640 atmospheres per mole fraction, so that we can estimate the maximum solubility of CO2 in the water, and the diffusivity of CO2 in water is given as 1.92 into 10 power minus 9 meter square per second, and interfacial area, that is 80 meter square per meter cube. That means if we have 1 meter cube of vessel, I will have 80 meter square contact surface area through which the mass transfer is occurring from the gas phase into the liquid phase, and the outlet gas contains 2.3 grams of CO2 per liter. Now what you have to do, we have to estimate the delta if film thickness is film theory is applicable. We have to estimate the contact time Tc if penetration theory is applicable. Then you have to estimate the rate of surface renewal if surface renewal theory is applicable. What we do now, We will try to see the problem here. The pure CO2 is entering here. CO2 is absorbed into the water. We are getting a water 2.3 grams per CO2 per liter. The undissolved CO2 is coming here, and we have 8 liters of dispersion, that is a gas and liquid. That means for every meter cube of volume, there is 80 meter square of interfacial area is there. So we are interested to estimate these 3 parameters. Now what we can do, we can estimate solubility of CO2 in water to atmosphere is X star, that is nothing but 2 by 1640, where 2 is the pressure and 1640 is the Henry's-law constant. That is where we are going to get 0.00122 mole fraction, 0.00122 mole fraction. That is the mole fraction of CO2 in the tank. Now we can estimate the molecular weight of solution. This molecular weight of average molecular weight of solution, this is nothing but, as we know, here carbon dioxide is there and water is there. The carbon dioxide mole fraction is this, and water mole fraction is 1 minus 0.00122. So we have to calculate the average molecular weight of the solution. That can be calculated as molecular weight of carbon dioxide multiplied by its mole fraction 0.122 plus the molecular weight of water, that is the 18, 1 minus 0.00122. That is nothing but 18.03, may be approximated as 18. So moles of the solution for meter cube of solution, moles of solution per meter cube. We know density of water, that is nothing but at a given condition 997 kgs per meter cube of density, and the molecular weight is 18.04, 18.03, 18. So we are going to get kgs per mole. So we are going to get it 55.4 kilomoles per meter cube. That means every 1 meter cube of solution contains 55.4 kilomoles of what do you call it, solution. And concentration of the CO2 leaving the vessel is 2.3 grams of CO2 per liter. That also can be written as 2.3 kgs of CO2 per meter cube of solution, and now divided with molecular weight, we are going to get 523 kilomoles per meter cube of CO2 in the leaving gas. Volume rate of input water, this is approximately equal to volume rate of output water, because at steady state, if you are going to see very small concentration of CO2 for a large concentration of water, so this will not changes much of the volume. So volume rate of input water is also almost equal to volume rate of output water, that is nothing but 1 liter per minute. So what one can say, this can be converted into 1.667 into 10 power minus 5 meter cube per second. Just we are using a conversion factor, that is 1000 liters is equal to 1 meter cube, and 1 minute is equal to 60 seconds. So the rate of absorption of CO2 in the vessel, you see, this is the volume for every second, and this contains, for every meter cube of volume, this many moles of CO2 is there. So the rate of absorption CO2 in the vessel is equal to 1.667 into 10 power minus 5 multiplied by 0.0523, that is equal to 8.718 into 10 power minus 7 kilomoles per second. V, volume of the dispersion, is given as 8 liters, that is nothing but 0.008 meter cube. So, and A is the interfacial area already given as 80 meter square per meter cube. So, rate of CO2 absorption, of CO2 at steady state is equal to V into volume into area into mass transfer coefficient KL into CS, that is CS is nothing but CS minus C, that is equal to, this can be, this is the equal. So, 8.718 to 10 power minus 7. From this we can estimate the mass transfer coefficient KL is equal to 8.903 into 10 power minus 5 meter per second. So, now we got the mass transfer coefficient. So, this is the way we are solving the problem, and once we know this mass transfer coefficient, then what we can do, we can estimate delta film thickness, that is equal to DAB by KC, DAB by KL, that is nothing but 1.92 into 10 power minus 9 divided by 8.903 into 10 power minus 5, that is equal to 0.0216 mm. This is the film thickness, that is the A bit. B bit, the contact surface area, contact time, that is equal to 4 DAB divided by pi into KL square, that is equal to 1.92 10 power minus 9 divided by 8.903 into 10 power minus 5, that is equal to 0.3083 seconds. Then the C bit, rate of surface renewal, S is equal to KL square divided by DAB, that is equal to 4 into 1.92 into 10 power minus 9 divided by pi into 8.903 into 10 power minus 5 whole square divided by 1.92 into 10 power minus 9, that is equal to 413 seconds. This means that the surface is renewed 4.13 times for every second. So, these are the three things we are able to calculate, and what we did here, we are able to estimate the mass transfer coefficient independently with the help of material balance. Just what we did is, we have not done anything at all. Just what we did is, we have estimated we have done some material balance, because we know how much of CO2 that is entering here, what is the quantity of water that is entering is known, and what is the quantity of water that is leaving. So, from this, for every 1 second, how much of carbon dioxide that is absorbed, that we are able to estimate. So, that is 8.718 into 10 power minus 7 kilomoles per second of CO2 is absorbed for every second. And now we know there is a 8 meter cube of dispersion is there, and this should be equal to your, as we know, V into A into KL into CS minus C, where CS is the, what do you call it, concentration at the maximum solubility limit that we have estimated from the Henry's law. So, that we have substituted, C is known to E and V and A are known to us. So, we are able to estimate the KL value. So, once if you got the KL value, we got the delta, we got the TC, and we got a S value. So, this is the one problem where it will explain you and how these three theories can be estimated, can be used for the calculations of the required parameters of delta, TC and S. Now, the next problem will be comparing using the correlation of your JH is equal to JD. Like the problem is this: a canvas bag commonly used for storing water in the deserts hold some quantity of water. A small quantity of which continuously seeps through the canvas pores and diffuses in the ambient air with the effect that evaporation of water cools the bag. The surface temperature of the bag is 291 degree Kelvin. What we have to do, we have to determine the ambient temperature of air on the basis of the following parameters at that temperature. So the parameters which are given as Prandtl number, that is equal to 0.72, and Schmidt number, that is equal to 0.61, and density of air, that is given as 1.15 kgs per meter cube, and specific heat of air, Cp of air, that is given as 1.048 kilojoules per kg degree Kelvin, and latent heat of vaporization of water is 2456 kilojoules per kg, and partial pressure of water in the ambient air is 1066.64 pascals. Right? So the issue is, we know we have a canvas bag. Generally, as all of you know, it contains a lot of pores, and maybe I don't know whether you have seen or not. When we don't have these refrigerators and all those things, people used to store the water in the canvas bag, and when you are traveling in a car, and if you are going to keep your canvas bag, I mean outside the car, because the car is going with high speed, so that means it is creating some sort of turbulence, and in the atmosphere the water concentration is 0, so the water will transfer or will permeate through the pores of the canvas bag and joins into the, what do you call it, atmospheric air. And for this sort of a permeation and evaporation, some energy is required, and that energy is supplied by the water itself by losing its sensible heat. So when it loses its sensible heat, so the water in the bag gets cooled, and that is the reason what one can see, we can sense it, the water temperature in the bag is less, and we can use it as a cold water. So this is what generally we do, and this is what people who are traveling in the deserts, they hold the water in a canvas cloth, and because of that there will be a permeation of water through the canvas cloth, then evaporation of water from the canvas cloth into the atmospheric air, and because of whatever the energy that is required for the evaporation of water, that is nothing but your latent heat of vaporization of water, is supplied by the water itself. So when the water is going to supply the latent heat of vaporization, and then the water inside the bag is going to be cooled, and that is where it is at a cold condition and at a low temperatures. So what we want to say now, there is a mass transfer, there is a heat transfer, there is a simultaneous mass and heat transfer problem. And to tell you one more example, I have a, let's say, maybe I don't know, nowadays as I told you, we are using a refrigerator, but when you go to the villages, we don't, some of the houses, they may not have the refrigerator, and at that time what they do is they store the water in a pot, and that pot is nothing but a mud pot. So when the water is stored in a mud pot, particularly in the summer season, right, it contains lot of pores, isn't it? It contains lot of pores, and maybe on the top of it we can put a small plate here, or we can even keep the plate so that more cooling is going to occur, but to avoid the contaminations and other things, we can keep the plate here. Now in the atmospheric, we have atmospheric air. In the atmospheric air, there is no, the concentration of water vapor is almost 0, because in the summer season the air is a dry air, so we will not have any humidity, so we will not have any vapor concentration in the air. And here there is a high concentration of water and there is a low concentration of water. So what will happen? The water will be evaporating, and the temperatures are very high. The water will be evaporating, or the water is permeating through that mud pot, because it contains lot of pores. So it comes to the surface. After coming to the surface, then because there is the concentration gradient or the chemical potential gradient is existing, the water will be evaporating. So whatever the energy that is needed for the evaporation of water is supplied by the water which is present in the mud part. And because of that, the water loses its heat in the form of a sensible heat. When water loses the heat in the form of a sensible heat, so the water temperature here is very less compared to the atmospheric air temperature. So that is the reason the water stored in a mud part is in a cold condition. And as you know, what is happening here, the heat transfer is occurring, mass transfer is occurring, and at the same time there may be some chances of, because it is the low temperature and there is a high temperature here, so the the mass transfer is taking place from the part to the air, and at the same time the heat transfer may take place from the air to the water which is present in the mud part. But this is the low thermal conductivity, the mud part is the low thermal conductivity material, and that is the reason it will not allow any passes of water, any heat through this. So that is the reason we can maintain at a low cold conditions. Maybe you can imagine a picture where instead of mud pot, if you are going to use the stainless steel vessel, and when you are going to store the water in a stainless steel vessel, in this case no heat transfer is taking place. But if suppose the vessel is stainless steel vessel and SS vessel, and suppose even this air is there, and now what is happening here now, this doesn't have any pores, so no permeation of water is taking place. So there is no reduction in the temperature. And at the same time what is happening here, so the temperature outside the vessel is very high, maybe little low temperature inside the vessel. Then what will happen, the heat transfer, there will be difference in the temperature. So because of this difference in the temperatures, the heat will flow from atmospheric air to the water which is present in the mud pot. And what is happening, ultimately there is no mass transfer is not taking place, but there is a heat transfer process. That is the reason the water which is stored in a stainless steel part will be at little higher temperature compared to the even atmospheric air. Then the third case that we can see, here we are using a mud pot. Maybe that mud pot is the old mud pot. Let's say this is the new mud pot, but now just imagine what will happen if the mud pot is the old mud pot. Now what is happening in the old mud pot, generally water will contains water and a salt, and continuously we are using the water, and along maybe the permeation of water is taking place, along with the water the salt also is going to move towards the surface here. When it reaches to the surface, because the pore sizes are very small, only the water will permeate through that, and the salt is going to be deposited inside the vessel. And when salt is deposited inside the vessel, then what will happen, as you are using continuously, there is a formation of the salt layer inside the vessel. When there is a formation of the salt layer inside the vessel, and some of the pores gets blocked, when some of the pores gets blocked, so then what will happen, the permeation rate is going to be decreasing. When permeation rate is going to be decreasing, the mass transfer rate is decreasing. Mass transfer rate is decreasing, the temperature, because when the permeation is decreasing, rate of mass transfer is decreasing, so the flux is decreasing. So what will happen, and then the water need not to supply large amount of sensible heat. So the temperature, and it is not going to lose the large amount of temperature. Because of that, what will happen, this water will be little higher temperature compared to the water which is present in the new mud pot. That is the reason in most of the villages, when you go to the villages would like to buy new mud pot every year. The reason is because salt is precipitating over this, and it is blocking some of the pores. When it is blocking some of the pores, the permeation rate is decreasing. Permeation rate is decreasing means the rate of mass transfer is decreasing. Once rate of mass transfer is decreasing, rate of evaporation of water is decreasing. Once rate of evaporation of water is decreasing, the energy required to evaporate the water is decreasing. When energy required to evaporate the water is decreasing, the reduction in the sensible heat is going to be reducing. When there is a reduction in the sensible heat, the temperature is little higher. So this is the reason villagers, they like to have a new mud pot every year, so that they can store the water and they can drink a water which is little cold temperature when compared to with the water which is present in the ambient conditions. So this is the same story. Even in this our problem, we have a canvas cloth or a canvas bag is there. We have stored the water in the canvas bag, and we just putting outside the car, and your car is going with a high speed. So that means what is happening, lot of turbulence is created surrounding to the car. So when the lot of turbulence is created surrounding to the car, then what is happening here, water vapor concentration is low here, and water vapor concentration is very high here, and at the same time, that means the concentration difference is there. In addition to this, we are providing a turbulence. When you are providing a turbulence, what will happen? The mass transfer coefficient is increasing. Mass transfer coefficient is increasing, the driving force is there. So because of this mass transfer coefficient and the driving force, so there is so much of mass flux is there. When there is so much of mass flux is there, so the water has to lose lot of its sensible heat. When the water is losing lot of its sensible heat, then the water temperature inside the bag will be very, very low, and this is generally travelers who are making a travel in the deserts. Maybe when you look at some drivers who are frequently traveling in the lorry, they cannot afford to buy the cold water. So what they do is they will store the water in a canvas bag, and they will put it outside their lorry, and lot of turbulence is created. There is a concentration difference. The temperature is going to be decreased. So the problem what it is given here, so the same problem it is given. This is the data what it is given here, and because as you know, we can apply the heat transfer correlation as we discussed in the morning. JH factor, the Chiltern-Colburn factor for the heat transfer is equal to JH factor for the mass transfer. That is JH is equal to JD. So JH is equal to JD. Now that is nothing but H by rho mu naught Cp Prandtl to the power of 2 by 3 is equal to Kc U naught Schmidt to the power of 2 by 3, and your Kc by H is equal to 1 by rho Cp Prandtl by Schmidt number to the power of 2 by 3. So this is the equation morning, and this is the equation I have given in the previous class. So now the same thing I am writing here. Now rate of mass transfer Na is equal to Kc into CAS minus CA infinitive, and rate of cooling is equal to Q by A, that is equal to H into T naught minus Ts, that is equal to lambda A MA into NA. Now where, as you know, that is, this is the heat lost by water for the evaporation of the water. That is also equivalent with the, as I told you, the mass transfer is taking place from the bag to the atmospheric air, and at the same time the heat transfer is taking place from the atmospheric air to the bag. So ultimately how much of heat that is received by the bag from the atmospheric air is equal to the heat lost by the water in the form of a latent heat of vaporization. So this is the heat received by the bag. This is the heat lost by the bag because of the evaporation of the water. And now we know this is Q by A is equal to H into T delta minus Ts, that is equal to lambda A into MA into NA. So H into T delta minus Ts, that is equal to lambda A MA, where Na is equal to Kc into CAS minus Ca infinitive. From this we can write H by Kc, or maybe we are interested about surface temperature Ts. So what we can write, T we can write as T infinitive, where minus T infinitive minus Ts is equal to lambda A MA Kc by H CAS minus Ca infinitive. And now this Kc by H is given by 1 by rho Cp into Prandtl by Schmidt to the power of 2 by 3. That we can substitute here, lambda A MA. So T infinitive instead of Kc by this one, 1 by rho Cp Prandtl to the power of Prandtl divided by Schmidt to the power of 2 by 3 into CAS minus Ca infinitive plus Ts. So now in this expression everything is known. So what one can do, we can plug the values whatever we have given, that can be plugged here. So we are going to get the T infinity value. So how to get this T infinity value now? Plugging the values here. T infinitive is equal to lambda A, that is 2456, MA, that is nothing but molecular weight of water 18, 1 by rho is 1.1532, and Cp, heat capacity, that is nothing but 1.0048, Prandtl to the by SC, that is 0.72 divided by 0.61 to the power of 2 by 3. Now the problem is here. CAS minus CA infinitive plus CAS minus CA infinitive. CA infinitive is nothing but the concentration of water vapor in the ambient air. As we know, there is no water vapor in the atmospheric air, so one can assume that 0. When it comes to the CAS, the partial pressure, that is the concentration of water at the interface. At the interface means this is the interface. At the interface between the liquid phase and the solid phase, in liquid phase and the gaseous phase, maybe there is a formation of the film of a liquid over the canvas cloth, and now it is evaporating. And what is the partial pressure that is given? 1064, and this is given in terms of pascals. And that we are, this pressure is given. We are interested to convert into the concentration. So we know Ca is equal to Pa by Rt, and now Pa is given as 1066.64 and Rt 8.8314, and temperature is given as 291 plus 291, that is nothing but your Ts. And if you see, this is going to become T infinitive, that is nothing but 308.78. That means T08 is 308.78, and here this is a Ts, that is equal to 291, and there is a difference of almost what do you call it as the 18 degrees centigrade difference is there between the ambient air and the surface of the canvas cloth. That is the reason, and 291 is almost equivalent with 18 degrees centigrade. So the water which is present in the canvas cloth is at 18 degrees centigrade. Obviously you can enjoy the water what it is present in the canvas cloth by drinking it. So this is during this what is happening, both mass transfer as well as the heat transfer is taking place. The mass transfer is taking place in the form of, here the concentration of water vapor is 0 here. There is a large concentration of water vapor is there on the outside of the cloth, because the cloth is having a pores. And how much of rate of mass transfer that is taking place? This is the rate of mass transfer that is taking place. Now when you talk about this amount of water has to be evaporated for every second. So the energy that is required is nothing but latent heat of vaporization multiplied by the flux. So here we are going to get in terms of moles. That moles is converted into the mass by multiplying with the molecular weight. So latent heat of vaporization multiplied by the molecular weight multiplied by rate of mass transfer. So this is the nothing but amount of energy lost by the canvas cloth in the form of a latent heat of vaporization. And when there is so much of heat, there is so much of temperature difference is there, there will be heat transfer from the ambient air to the canvas cloth, and that is given by heat transfer coefficient minus multiplied by T delta T infinitive minus Ts. So what we did is, remaining thing is a mathematical jumbling. Only this we have to understand. This is the two steps you have to understand. Other than that, remaining things are so simple, and that is where we have estimated T infinitive is equal to 308 and surface temperature is equal to 291. This is the way one can cool the water which is present in the ambient air, and this really clearly explain about the application of a chemical engineering to which generally we come across in the day-to-day problems. And the same problem what we are going to use for the explaining about the dry bulb temperatures and wet bulb temperature, maybe that we can discuss at a later stage of a time when we are discussing about the humidification chapter. But the thing is, this problem is clearly telling you the interest, application of chemical engineering to solve the real-time problems, right? Then the next problem is, a stream of air is flowing at 30 meters per second over a 2.25 meter cube thin square plate of a solid naphthalene. Determine the rate of sublimation from the plate. The air and the plate are at 25 degrees centigrade. The diffusivity of naphthalene in air at 0 degrees centigrade and 1 atmospheric pressure is 514 into 10 power minus 6 meter square per second. And the vapor pressure of naphthalene at 25 degrees centigrade is 25 pascals. The viscosity of air is 1.85 into 10 power minus 8 kgs per meter per second. So here what we have, this is what we are discussing yesterday. We have a square plate, square with a blackboard and like this, right? And air is flowing over the plate, but this plate now is not a stainless steel plate. This plate is now made with the naphthalene. So when air is flowing over the naphthalene is dissolved into the air. The naphthalene sublimates or the vaporizes and joins with the air. What it is given, the air and the plate are 25 degrees centigrade. And further it is given as this, maybe I can sketch like this. So this is the square plate and 2.25 area, 2.25 meter square area. That means your length of the plate is 1.5 meters. Then the DAB value is given as 514 into 10 power minus 6 meter square per second, right? And PSAT, that is given as 25 pascals. Then viscosity is given as 1.85 into 10 power minus 8. The velocity is 30 meters per second, and PT is given as 1 atmosphere. Temperature 298 degree Kelvin. So this is the data that is provided, and air is flowing over the naphthalene plate, and the naphthalene sublimizes and naphthalene evaporates, joins into the air. And what you have to do, we have to calculate, determine the rate of sublimation, how much of naphthalene is sublimizing into the air. This is the problem that we generally come across. Maybe when we are storing the clothes in a almirah, we put some sort of a naphthalene balls to avoid the insects and other things. So what is happening? After some time, maybe a month or 2 months later, we don't find any naphthalene ball, because what is happening? There is a evaporation, or there is a sublimation of a naphthalene into the air. Then we are going to use the fresh balls, and this is what even we do in wash basins. We use some sort of a naphthalene balls, and what is happening? There is a sublimation is taking place. What you have to do? We have to find out the rate of sublimation. To find out the rate of sublimation is nothing but you have to find out the rate of mass transfer. We have to find out the rate of mass transfer. So all the data are given here, and we have to find out the parameter called as we know, Reynolds number, NRE, that is nothing but L into U into rho by mu, and where L is nothing but 1.5, that is because, as I said, 2.25 meter square is the area, so your length is going to become 1.5 meters. So your length is nothing but this 1.5, and U velocity is 30 meters per second. And when it comes to the density data is not given, but we can calculate the density data. P is equal to, rho is equal to Pm by RT, where P is equal to 1 atmosphere, and M is nothing but 29, that is the air molecular weight, and R value 1 into 22.4 divided by 273. Maybe you can calculate straight away R value, or maybe generally what I suggest to many of the students, don't remember the value of R, because you know 1 mole of substance at 1 atmospheric pressure at standard temperature and standard pressure occupies 22.4 liters. That is your PV is equal to nRT. That means your R is equal to PV by NT, and according to your law of Avogadro, what it says, 1 mole of any substance at standard temperature and standard pressure occupies 22.4 liters. So now that is the pressure is 1 atmosphere, and this is the volume 22.4 liters, and this T is 273 multiplied by 1. So that is the R value of R. So you can remember the value of R whatever the way you like it, or this is one way of calculating the R value. Then T is equal to 298 degree Kelvin, and maybe this now we are going to get 1.18 kgs per meter cube. So now 30 into 1.18 divided by the viscosity is given as 1.85 into 10 power minus 8. So this is going to becomes 2.88 into 10 power 9, and we have discussed in the last class, if Reynolds number is greater than 5 into 10 power 5, 5 into 10 power 5, the flow is a turbulent flow. So we can use the correlation to use the mass transfer coefficient value. Now the flow is taking place in the turbulent flow and the geometry is square plate. So we have to take the correlation from the literature where flow conditions are given as 2.88 into 10 power 9 and the flow geometry is a square plate. So we have a set of equations, as I told you, there is a table number 3.1 in the textbook written by the Tribal, where we can take the correlation and we can do the things. Now Schmidt number NSC is equal to mu by rho DAB, that is equal to 1.85 into 10 power minus 8 divided by 0.114, rho is nothing but 1.14 into 5.14 into 10 power minus 6. So this is going to becomes 0.0315, and for this situation, as I said, Sherwood average divided by Reynolds to the power of 1.03 into Schmidt to the power of 1 by 3 is equal to 0.023 into Reynolds to the power of minus 0.2, right? This correlation we got it from the standard literature for a flow geometry of square and a flow condition of this Reynolds number. For this is the relationship one can use, and from this one can estimate Sherwood average is equal to 52172.15, and that is also equal to kg into ppm ln ppm, that is nothing but ppm, r into t into l pt into dab. Now we know pb1 is equal to 1 minus pa1, and pa1 is given as 25 pascals. So this is going to become 0.9997 atmosphere. pb2 is equal to 0. That means a large quantity of air is flowing here, and there will not be any concentration, or the concentration of naphthalene in the flowing air is 0. So that means Pa2 is equal to 0. So Pb2 is equal to 1 atmosphere. So from this one can estimate a Pb ln, that is going to become 0.9998 ppm. So we can substitute now everything. So kg is equal to 172.15, Pt is equal to 1 atmosphere, dab is equal to 0.5 into 14 into 10 power minus 6 divided by kg is equal to, and ppm is equal to 0.9998, and r is equal to 82.06, that is, and temperature is equal to 298, and L is equal to 1.5, that is equal to 2.636 into 10 power minus 8 kilomoles per meter square per second per atmosphere. And your flux Na is equal to kg into Pa1 minus Pa2, that is equal to 2.636 into 10 power minus 8, where Pa1 is equal to 25 pascals divided by 1.013 into 10 power 5 pascals minus 0. We are converting pascals into atmospheres here. So here we are going to get it 6.504 10 power minus 12 kgs per meter square per second. Right now, you try to understand the significance of this value. That means if you take 1 meter square of naphthalene's plate, for every 1 second there is a 6.504 into 10 power minus 2 12 kgs of naphthalene is evaporating. So if you know the total plate, if you know the total weight of the plate, then we can tell what is the time that is required for the entire evaporation of the plate. This is what I told you in our module number 3 or module number 4. What is the need for the estimations of the flux? The need is for any purpose. Without that we can't do anything. For example, as I told you, when you are going to purchase your bathroom freshener, and when you keep it in a bathroom, and we should know how long it is going to last. Then after that you have to purchase it. Maybe the people who doesn't have the knowledge of the chemical engineering, what they do, just they will every day they look at your bathroom freshener and see whether everything is there or it is exhausted. But when you belongs to chemical engineering, and when you know your velocity, and when you know your concentration, and when you know area of the bathroom, so we can find out how much of time that is going to be there. Maybe after that what you have to do is you have to buy a new one. So that is what we are going to do it. And one more thing that you can understand, when bathroom windows are closed, then the rate of loss will be less. If bathroom windows are open, because the atmospheric air is blowing outside the bathroom, so there is whatever the freshener evaporated, that goes through the windows and joins into the atmospheric air, and there is more rate of loss will be there regarding that. So this is the one example where we are going to come across in day-to-day life. Maybe that is where you can appreciate the importance of the mass transfer operation. So the next question is, so this problem is, a certain quantity of ethanol accidentally spilled over on a smooth tabletop in a laboratory. The laboratory exhaust fan produced an airflow of 655 centimeters per second, parallel to and over the table surface, flowing across 1.25 meter wide tabletop. The air temperature was steady at 289 degree Kelvin, and its pressure was 1 standard atmospheres. The kinematic viscosity of air is given as 14.8 into 10 power minus 6 meter square per second at 289 degree Kelvin. The vapor pressure of pure ethanol is 4000 newtons per meter square at 289 degree Kelvin, and the diffusivity of ethanol in air at 298 degree Kelvin and 1 standard atmosphere is 13.2 into 10 power minus 2 meter square per second. Determine the rate of evaporation of ethanol per meter cube of tabletop. This is the problem generally we come across when you are working in a laboratory. So if any chemical spilled on a floor, right, then you have to remove that chemical before your teacher enters into the laboratory. Otherwise, as you know, your teacher is going to scold you. One thing that we can do, we can take a piece of cloth, then we can wipe it out with that cloth and throw the cloth. But the problem is, in a laboratory we are going to come across different chemicals. Maybe that chemical is toxic. We cannot use our hands to clean the floor. At that time what you have to do, somehow you have to remove whatever the chemical that is spilled over the floor before your teacher enters into the laboratory. For this, what one can do, just leave it like that for some time, because your chemical is a highly volatile substance, and it vaporizes and it joins with your air, and ultimately your floor gets clean. But the problem is, as I told you, when you are not using any external agency, or when you are not using any external agents, then what will be the problem? The problem is your molecular diffusion is going to take place. The molecular diffusion is a very slow process, and maybe takes long hours, maybe day or maybe 10 days or 15 days time it is going to take, just if you leave the as it is. To avoid this type of thing, what generally people will do, they will use the exhaust fan. Maybe they will switch on the fan. When the fan is switched on, there is so much of turbulence is going to be created, and as you know, the mass transfer rate of mass transfer is very high, mass transfer coefficients are very high. So whatever the thing that is evaporated, because of the turbulence, the mass because of the high mass transfer coefficient. Mass transfer coefficient is high. The there is some driving force is there. So your rate of mass flux will be very high, and because of that, within no time we can remove whatever the chemicals that are spilled here. So this is the one interesting problem. That's what we are talking about. A certain quantity of ethanol accidentally spilled over on a smooth tabletop. So we have a smooth tabletop. On this, ethanol is spilled, and this is the 1.25 meters wide plate, and the air is flowing over this. We are putting the exhaust fan here, and air is flowing here. So what we have to do now, we have to estimate how much of time, what is the rate of evaporation of ethanol per meter cube of tabletop. So what we do now, the step one, what we can do, the diffusivity value here, the data, what the data is given, the new value is given, that is nothing but a kinematic viscosity, 14.8 into 10 power minus 6 meter per second, and PA-sat, that is the vapor pressure of ethanol, is nothing but 4000 Newton per meter square, and the DAB, diffusivity of ethanol in air, this is given at 298 degree Kelvin, that not at 289 degree Kelvin, where our working temperature is 289 degree Kelvin. So that is nothing but 13.2 into 10 power minus 6 meter square per second. Now we have to estimate the diffusivity at 289 degree Kelvin. Diffusivity at 289 degree Kelvin, that is nothing but DAB, temperature T2 is equal to DAB at temperature T1, T2 by T1 whole to the power of 3 by 2, P1 by P2, and 13.2 into 10 power minus 6. T2 is 289, and T1 is 298, and P1 and P2 are 1 by 1. So this is going to become 12.606 into 10 power minus 6 meter square per second. So your Schmidt number is equal to rho by DAB, nu by DAB, that is equal to 14.8 into 10 power minus 6, 12.606 into 10 power minus 6, that is equal to 1.174, and your Reynolds number RE is equal to VL by nu, that is equal to 6.55, your L is 1.25, that is a wide, divided by 14.8 into 10 power minus 6, 5.532 into 10 power minus 10 power 5, which is greater than 3 into 10 power 5. So certainly what will happen, there will be a transition from a laminar flow to the turbulent flow. So we have a, as we discussed in the last class, we have a leading edge here. So from the leading edge up to certain distance, the flow is in the laminar flow. After that, the flow is going to become a turbulent flow. So what we have to do now, we have to find out what is that transition point. The transition point can be estimated as L transition, that is equal to Reynolds number transition multiplied by nu by V, that is equal to 3 into 10 power 5, 14.8 into 10 power 6, 6.55. Do you understand that? Now this Reynolds number is 5.532 into 10 power 5, which is greater than 3 into 10 power 5. As we discussed yesterday, up to 3 into 10 power 5, the flow is in the laminar flow, above which the flow is going to become turbulent. So that means up to certain distance, the flow will be in the laminar condition, above which the flow is going to become a turbulent flow. So what we are interested to find out, up to what distance we have a laminar flow conditions are existing, and above which the flow is going to become turbulent. So we are estimating LTR that is the transition point where things are changing from the turbulent laminar flow to the turbulent flow. This is the expression that we are using, and it is becoming 0.6778 meters. That means I have a total length of 1.25 meters. This length, out of this up to 0.6778, the boundary layer, within the boundary layer, the flow is a laminar, above which the flow is turbulent. And as you know, maybe we can, when you talk about your Prandtl theory, what the Prandtl theory says, Prandtl analogy, the Prandtl analogy takes into the account of both laminar flow as well as the turbulent flow. So we are going to estimate the mass transfer coefficient now. That is nothing but mass transfer coefficient, correlation for the mass transfer, estimation of mass transfer coefficient for the laminar flow condition, correlation for the estimation of mass transfer coefficient for the turbulent flow condition. That is 0.664 into DAB into Reynolds transition to the power of 0.5, Schmidt number to the power of 0.33 plus 0.0361 SC to the power of 0.33, Reynolds number REL 0.8, RE transition 0.8. So this is for the laminar flow, this is for the turbulent flow, and up to this the flow is the laminar flow, and this minus this is applicable for the turbulent flow, whole divided by 1.25, and that is going to become 9.0754 into 10 power minus 3 meters per second. This is your mass transfer coefficient. And now ethanol evaporation rate, that is nothing but W, that is equal to Kc bar into area for the flow, area perpendicular to the flow, multiplied by CAS minus CA infinity. And if you are interested to estimate the CAS, that is the concentration of ethanol at the interface between the liquid and the fluid, and the liquid and the gas, that is nothing but CAS, that is the pressure 4000 divided by R into T, and that is going to become 4000 divided by 8.314 into 289, that is going to become some value, we will leave it like that, and Ca infinity, that is the ethanol concentration in the bulk of the air, one can assume as a 0. So we know now rate per area, W for area, that is equal to 9.7054 into 10 power minus 3 into 4000 divided by 8.314 into T 289 minus 0, that is going to become 16.1571 into 10 power minus 3 moles per second, that is going to become 26.75 kgs per hour. So if 1 meter square of area is there, if you switch on the fan for 1 hour, then there will be evaporation of 26.75 kgs of ethanol. So once if you know the volume of the ethanol, we can calculate the mass of the ethanol. Once if you know the mass of the ethanol, and suppose if you assume that the tabletop area is 1 meter square, and for 1 meter square tabletop area, for every 1 hour this much of ethanol is going to be evaporated. So once if you know the quantity of the ethanol, maybe let's say there is a quantity of 26.75 kgs. So that means it requires 1 hour time to remove the entire amount of the ethanol. So we have to see that before that your teacher is not going to come. And this is what the problem, and what I am going to do now, I can give you some more problems as an assignment, and once if you make a practice of those problems, you will understand the concepts of chemical engineering. Then once if you solve those problems, really you can enjoy the chemical engineering subject, and we can also learn about mass transfer coefficient, once if you are going to learn about mass transfer coefficient, it is easy to understand the heat transfer process, it is easy to understand the momentum transfer process. As we know, the chemical engineering is nothing but momentum transfer, heat transfer and mass transfer. So that is where we are going to learn everything about the chemical engineering. So what I do is, I can give you some assignment problems. So there you can we can do some sort of a practice, then you will get a lot of command over the chemical engineering. Thank you very much.